So far in this chapter, we have learned how to find derivatives of a few different types of functions. We found how to do derivatives of polynomials. We learned how to do derivatives of trigonometric functions, sine and cosine. We learned product rule, chain rule. Actually, we might not have done sine and cosine yet at this point, but we've learned a whole bunch of rules, and those all work really, really well when you have f of x equals some function of x equals stuff, or y equals stuff. Now, there's this whole other category of problems, though, that are not easy to reduce down to simply just a function of x or to get y by itself. And so we need to be able to find derivatives of more complicated functions or relationships so that we can find slopes of tangent lines for any type of relationship. And that's where implicit differentiation comes into play. Because like an ellipse, x squared over a squared plus y squared over b squared equals 1, that is not a function, and it's not simple to just get y by itself sometimes. But we still want to be able to find the slope of a tangent line at any point along that ellipse. So here's where implicit differentiation comes into play. I'm going to write out an equation real quick, and then I'm going to talk about how we approach this from a implicit differentiation standpoint. So let's say we have the relation x cubed plus y cubed equals 6xy. Now, this would not be a simple thing for us to solve for y. So rather than trying to do that, we're going to do implicit differentiation. So implicit differentiation, as we take a look at this, we take the derivative of x's just like we did for anything else. The only difference then is that we sort of treat y kind of the way that we do x's, but we have to keep in mind that y itself is like a function of x. So when you have y cubed, we have some sort of function cubed. So what that means, as we approach this equation, moving from left to right, is that, well, the derivative of x cubed, that's easy. That's 3x squared. And you know what? The derivative of y cubed itself is even fairly easy because it would just be 3y squared, just like the x cubed. However, since y itself is a function of x, what we have to do then is do chain rule, where we take now the derivative of y and multiply by it. So we did the derivative of something cubed, which is 3 times the something squared, times the derivative of the something, or y prime. You could also write it as dy over dx, or there's a few different variations on that. But in this case, I'm just going to use y prime because it's simpler to write it that way. Now equals, well, 6xy. Okay, so 6x times y. I'm gonna take this as a product rule where 6x is u and y is my v value. So the derivative of the first part, u prime, would be just 6. So u prime v plus u, 6x, times, well, the derivative of y, we've already talked about, is y prime. Now, you can think of it as being 1 times y prime, but the derivative of just y itself is just always y prime. Now, the next thing that we want to do is we want to get all of these y primes on the same side of our equation here so that we can then factor it out and actually get it by itself. So, to that end, I'm going to subtract 6xy prime from both sides. And I'm also going to subtract this 3x squared from both sides because I want to get rid of that over on the left. So this cancels here. This cancels here. You can probably hear my children in the background. They are a bunch of savages. No offense to actual savages. Very nice people from what I hear. So we've got 3y squared y prime minus 6x y prime equals 6y minus 3x squared. Now, what I said is that I'm going to then factor out a y prime. So factoring out a y prime, that goes away. And then what I can do is I can divide both sides by 3y squared minus 6x. divided by 3y squared minus 6x. And so that cancels with that. And we end up with y prime equals 6y minus 3x squared over 3y squared minus 6x. Now, if you wanted to take one extra little step here, we could continue on and divide everything by 3, or like factor out a 3 over here, and that becomes a 2, and that goes away. And if I factor out a 3 here, that goes away, and that becomes a 2. And then these cancel each other out. And what we'd be left with is 2y minus x squared over y squared minus 2x, and I'm pretty sure that's all the simplification that we can do. So y prime, or also dy over dx, our derivative function, our derivative relationship, is 2y minus x squared over y squared minus 2x. So that's essentially what you do with implicit differentiation. You move across your equation from left to right. You treat x's just like you always did. Whenever you run into a y, you take the derivative of it, assuming that it's like a chain rule. If it's just y by itself, then the derivative is y prime. But if you have y to any power, or if you have like the sine of y, the derivative of the sine of y would be cosine y, but then you always have to multiply then by a y prime at the end because of the chain rule. I hope this video helps. It's not really that complicated of a concept. Same rules apply. Oh, and you know what? One last little thing. They might ask you what is the slope at a given point. So, if they gave you a point like 1, 1, and they said, what is y prime when at this point here? And all you would do then is take that x value and that y value and plug it into this formula here, and it'll give you some number. So, for example, 1, 1. So 2 times 1 is 2, minus 1 squared is 1, so 2 minus 1 is 1, over y squared would be 1 minus 2 times 1, so 1 minus 2 would be a negative 1, so my slope at that given point would be a negative 1. If you have any questions, let me know.